Ladies and gentlemen, welcome to the PhD graduation ceremony of welcome to the PhD graduation ceremony of Institut Polytechnique de Paris class 2023. To host the ceremony of graduation. I'm Madi Manager Taibi, and I have the honor to host the ceremony of graduation. Warm congratulations to the talented graduates. First of all, I want to extend my warm congratulations to the talented graduates, which bring remarkable values to the society. Now you carry remarkable values to the society. Doctor, now you carry two prestigious titles. Many people are proud of you, and you should be proud of yourself. Many people are proud of you, and you should be proud of yourself. Without the explicit and reaching at this point wouldn't be possible without the faculty and staff of Institut Polytechnique de Paris. So I want to introduce you of Institut Polytechnique de Paris. Acting President of Institut Polytechnique de Paris. Please welcome to Professor President of Institut Polytechnique de Paris. Please welcome to Professor Thierry Collomb.
Bonjour à toutes et à tous. Hello everybody. I'm Thierry Collomb. Bonjour à toutes et à tous. Hello everybody. I'm Thierry Collomb, President of the Institut Polytechnique de Paris. It's my privilege to open this graduation ceremony. As I was supposed to. I won't deliver an opening speech remarks, as I was supposed to. I will rather deliver what you are talking about. But let me just tell you that it's a very important moment for you. Obviously, it's a rite of passage, and as all rites of passage, it's extremely meaningful, and we'll do our best to make it meaningful for you. And the second point is, it's an important moment for me, not only because I'm very proud to be the president of the Institut Polytechnique de Paris, but also because it reminds me of my stint in Australia, where such ceremonies were the peak of the academic year. So I'm sure, again, I'll be more inspired after having listened to you, and let the celebrations begin. Madi.
Thank you, Professor Collomb, for your meaningful speech. Now it's time to introduce you the Vice President of Research at Institut Polytechnique de Paris, Professor Kees van der Beek. The floor is yours.
Thank you very much. Today is a day of great joy. You have come at the end of a very important journey in your life. It is a day of joy because you're here with your family, with your loved ones, your dear ones. And it is also a day of joy because you have known the excitement of research, of understanding, of the feeling of what it is to discover, to, on that journey, to tread where no one has gone before, and in doing so, push the limits of science and push the limits of human knowledge, and I believe it is a great thing indeed. So congratulations for that. It is also a day of achievement. You took a doctoral project, a PhD project, a scientific project, followed it through to the end. There were many hurdles. You may have changed your bearings, your direction, changed the plan entirely, but here you are, and the plan, the project has been done, and it is a great achievement. In having achieved it, you are now independent scientists, as the doctoral diploma sanctions, as it is, rewards you for having made this particular achievement. It is also a day, I would say, of great responsibility, because now your professional career is starting in earnest, and as is materialized by the oath that now the promise that each and every one of you makes at the end of the PhD, it is an extreme responsibility to observe good scientific practice, sound practice, honesty in whatever is delivered in the practice of research, and to do so in the remainder of your academic and scientific life, but also professional life elsewhere, should you choose not to pursue academics. It is a day of pride. You are now embarking on a new journey, which I mentioned. It is one of your career. And on this journey, You will bear the colors of being an alumnus of Institut Polytechnique de Paris. That is of great pride to us as an institution. You are our ambassadors in the world from now on. You will be the ones who will knit our increasingly large and important scientific network. It is extremely important for you, for us, to grow your network of professional and scientific relations. And we would be very glad to hear from you and to work with you in the future if that would be possible. So with this, it is also a great pride for me to be here in front of you. We have made these achievements. It is a great thing, and I warmly wish to congratulate you all for what you have done in the past 3-4 years. Thank you very much.
Thank you, Professor Kees van der Beek. I totally agree that the journey has just begun. Now it's time to introduce you Professor Adriana Tapus, the Director of IP Paris Doctoral School, and Professor François Rueff, Deputy Director of Hadamard Mathematical Doctoral School. Please.
Okay. So thank you, Thierry and Kes, for your presentation, and Madi for your introduction. So as you may know by now, I think so, I hope, I am Professor Adriana Tapus, the Director of the Doctoral School of Institut Polytechnique de Paris, and together with my colleague, François Rueff, the IP Paris representative of Hadamard Doctoral School of Mathematics, we would like to extend our warmest congratulations and welcome you to this IP Paris PhD graduation ceremony. So today marks a significant milestone in the lives of 271 remarkable individuals and new doctors that you are. It is with great pleasure and pride that I extend my heartfelt congratulations to each of the new doctors receiving their doctoral degree today. So this includes 221 graduates from the Doctoral School of IP Paris and 50 from the Hadamard Doctoral School of Mathematics. Among you, you are like 85 women and 45 international PhD graduates, adding to the diversity and richness of our academic community. Today is indeed a day of celebration, and I'm certain that many of you are joined by your family members, friends, partners, and spouses who are equally proud and thrilled to be part of this memorable IP Paris PhD graduation ceremony. The journey to this point has been long and challenging. Over the past several years, you have focused deep into your chosen research fields, spending countless hours in research, analysis, and innovation. Your dedication and hard work have culminated in the achievement of earning a doctorate from IP Paris, a university recognized globally for its excellence. This accomplishment is a testament for your resilience, intellect, and unwavering commitment to advancing knowledge. As we celebrate your achievements today, it is important to acknowledge those who have supported you along the way, to the families and friends who have offered their encouragement and understanding. Your support has been invaluable. We also extend our deepest gratitude to the professors and supervisors who have guided you, providing exceptional education and mentorship, and helping you to develop your research capabilities. So the dedication has played a crucial role in your success. Now, as you step forward as newly doctors, you may find yourself contemplating what has changed since you first began this journey. Okay, so let me highlight 3 significant transformations. The title of doctor is the first one. Okay, you now hold the esteemed title of doctor, a recognition of your expertise and research contributions. People can call you doctor, even though you cannot prescribe pills and fix broken bones. Your independent research capabilities is another step forward. With a doctoral degree from IP Paris, you have attained the highest level of academic qualification. You are now equipped to pursue independent research, contributing new knowledge and innovations in your field. And finally, your strong scientific foundation. Throughout your doctoral journey, you have built a robust scientific foundation. So these prepare you to face new challenges in your professional life with confidence and competence. So the degree that you receive today from IP Paris not only recognizes your past achievements, but also equips you for future endeavors. As you move forward, I encourage you to embrace new horizons with confidence. Your capabilities and research skills are your tools for success. Do not fear the unknown, instead view it as an opportunity to apply your knowledge and skills in new and innovative way. Stay positive, be resilient, and always take pride in your degree and your alma mater, IP Paris. In closing, I would like to leave you with an inspiring thought from Albert Einstein. Innovation is not the product of logical thought, although the result is tied to logical structure. As you venture into the future, believe in your dreams, harness your potential, and make a meaningful impact on the world. Congratulations once again to each of you. May your journey ahead be filled with success, fulfillment, and endless possibilities. Thank you.
Thank you, Adriana, for this beautiful speech. And I just want to add my voice to the congratulations for everybody. And you should hold the...
Yes. And so now I would like to ask all the responsible of research field from the doctoral schools to come here on stage.
Thank you, Adriana and François, for the talk. Really beautiful costumes. I'm jealous. I hope I can have one of them in the near future. IP Paris has always been pioneer in supporting women in research. Today, we want to introduce you one of these successful women in research. Anne Canto, who is the Director of Research in Cryptography, working at INRIA Paris. She earned her diploma in engineering from ENSTA Paris in 1993, and she completed her doctorate at Pierre and Marie Curie University in 1996. She is a worldwide well-known researcher. Dr. Cantu was awarded the Legion of Honor in 2019. She was awarded the 2023 Woman Scientist of the Year by the Irene Joliot-Curie Prize, and she became a fellow of the International Association of the Cryptology Research in 2024. Thank you for accepting our invitation as keynote speaker for IP Paris PhD Promotion 2023. The floor is yours.
Thank you very much for this invitation. It's a great pleasure to be here today because I am an alumnus of ENSTA. And, well, this was a different building, this was in Paris, but ENSTA played a major role in my career. First of all, because when I arrived at ENSTA, I didn't know at all what I wanted to do. Well, actually, there was a single thing I was sure. This is that I didn't want to learn and to study computer science. And so this is one of the motivations why I choose ENSTA, because there was no word like computer or telecommunication in the name. But when I arrived, during the first year, we had many courses on operating systems, on programming languages, on algorithm, and then I realized that computer science was a science, like mathematics or physics. Well, and nobody had told me that before. And so it was a science, and I loved it. And also, ENSTA gave me the opportunity to do several internships. And during the first internship, then I discovered research in a physics laboratory in Orsay. And then I came up with the idea of doing a PhD in some area with both mathematics and computer science. And this is how I started a PhD in cryptography. Well, there's a last point, which is a bit different, but which was also important, which is the fact that at that time, there were some PhD grants for ENSTA students. This was from a doctorate program funded by DGA, and so it means that it was a bit easier because I only had to find a PhD advisor. I didn't have to apply for funding. So you can now understand why I said that ENSTA played a major role in my career. And I hope it's still possible now for students for, I would say, undecided students like myself to have this kind of career. So let me now tell a little bit and talk a little bit of my research area. So my research area is what we call cryptographic primitives. So cryptographic primitives were building blocks in security protocols. So just to try to make things a bit more visual, I represented here a security protocol, which is, as an example, the protocol which is used for encryption in signal messaging app. So what is important here on this picture is that you can see that such a protocol, it consists of communications between the different parties, and also it consists of some transformations of the data, and these transformations are represented on the scheme by these yellow and pink boxes. And these boxes, these are exactly what we call cryptographic primitives. So they correspond to transformation with very specific properties and very specific functionalities. And so I show you this picture because what is very important is that analyzing the security of the protocol and analyzing the security of the cryptographic primitives, they rely on two very different approaches. Because for analyzing the security of the protocol, what we do is that we use a model where the primitives, these boxes, they have an ideal behavior. And so we make proofs. We prove that we have the required properties in this ideal model. Right? So that means under the hypothesis that the primitives are ideal. Well, my role as a cryptographer is to instantiate these ideal boxes and to estimate how these real-world primitives now differ from ideal boxes and do not have an ideal behavior. So, well, just to give you an idea, well, let me talk about the most widely used primitive, which is the one we use for encryption, so for protecting confidentiality of messages. So suppose that Alice wants to send to Bob a confidential message. What she will do is that she will transform it with what we call an encryption function. So the original message, this is what we call the plain text, and its image by the encryption function, this is the ciphertext. And so Bob then received the ciphertext, and Bob, because he is a legitimate user, he knows a secret which enables him to decrypt and recover the original plain text, right? So this secret, this is called the decryption key, and of course, because we have a decryption key as a parameter of the decryption function, then we also have a parameter of the encryption function. So there are some situations where these two parameters are the same, and these systems are called symmetric systems, and this is the systems I'm working on. But there are also some situations where the encryption key is different from the decryption key, and in that case, we talk about public key cryptography because the encryption key is public. And so the security property, what we need here, is that an eavesdropper who will intercept the ciphertext won't get anything about the plain text, any information. And so this property, this has been formalized by Claude Shannon, who's the father of information theory. And so what Shannon says is that what we want is that if once after the ciphertext has been intercepted, then the a posteriori probabilities of each plain text, that means the probabilities of each plain text, once we know the ciphertext, these probabilities were the same as the a priori probabilities. This means without knowing the ciphertext. In other words, this means that the plain text and the ciphertext were statistically independent. And so an equivalent formulation is that for any intercepted ciphertext, the probability that the decryption of this ciphertext leads to a given plain text M, this is exactly the same, it has exactly the same value for any possible plain text. And then because of this formalization, Shannon was able to prove this well-known theorem, which is a necessary condition for perfect secrecy. This was a definition of perfect secrecy. And so what Shannon proves is that for a cipher to be secret, a necessary condition is that the number of secret key must be greater than or equal to the number of possible plain texts to be encrypted. So, and we usually, well, say in a simplified manner that this means that the length of the secret key must be at least equal to the length of the plain text to be encrypted. So what it means is that this condition, of course, it's impossible to satisfy it in practice, except for very, very particular applications. It's impossible to exchange a secret, which is as long as the messages we will have during our communication, like videos or images and so on. So this implies that for all systems that we are using in practice, this condition of perfect secrecy, it does not hold, it's not satisfied. So the relevant question that we have as researchers in cryptography when we want to analyze the security of a cipher, this is not to know whether it is perfect or not, because we know it's not perfect if it's a practical cipher. So the relevant question is to measure, to evaluate the cost for breaking the cipher, because we know that, in theory, it's possible to break it. So breaking the cipher means recovering the plain text from the ciphertext, or even better, recovering the decryption key, right? And so this work of trying to attack the cipher and estimate the cost of the attack, well, this is what we call cryptanalysis, and this is something which is essential. This is the only way we can guarantee the security of our cryptographic primitives. And this is the only way we have to dimension the system and to evaluate the security margin. So how does it work in practice, this cryptanalysis? Well, there's an example that you probably all know, which is cryptanalysis of the Enigma machine and other a German ciphering machine during World War II. Well, this example is, of course, very famous because it has motivated the construction of the very first programmable and electronic computer in the world. And well, things are I think, quite different right now. We do not break the Enigma machine, but there's one thing which I believe is similar. This is the fact that this project on cryptanalysis, the Enigma machine, it was successful because of a major ingredient. Of course, we always mention Alan Turing in this story, but there was something which was very important, which is the fact that there was a collaboration between many people with many different backgrounds. Mathematicians, people working on what we could call computer science, cryptanalysts, but also chess champions, also linguists, and people with many different backgrounds. And I think that it's something which is important more generally for research, that for research, this kind of diversity, the fact that we have collaboration between people with very different backgrounds, this is something essential for the success of research. Because, well, great ideas usually come from confronting different point of views, and for having different point of views, we usually need having different backgrounds. So, we are not working on the Enigma machine anymore, of course, so what happens nowadays? How do we know that our cryptographic primitives, the one that you are using in your mobile phone or on your computer, that they are secure? Well, this means that we need to guarantee that there was some cryptanalysis on this, so how do we guarantee that these primitives have been scrutinized and studied by many people? And so the answer is that, well, before defining a standard primitive, what we do is that we usually organize a public and open competition. So to give an example, like 15 years ago, NIST, which is the American Institute for Standards, they decided to define a new standard for hash functions. So, well, you don't need to know what a hash function is, but, well, it's just to show you that the way we did that, we defined this new standard, is that NIST, they launched a public competition. Well, they published a call for proposal, and they asked everyone to submit a candidate to this competition. So in this call for proposal, they defined the required property, the parameters of this hash function. And so many people, well, 64 teams, they submitted a proposal to the NIST. So submitting a proposal here means, of course, sending some specification of a function, but also implementations and also a document explaining the design choices and also giving some security arguments. And so, after, well, a first round, NIST found that only 51 among these 64 proposals satisfied the requirements, and then they published all the specification and they organized a conference where each team presented its proposal. And then, afterwards, well, we can start attacking. Well, because you know, when you are a designer in such a competition, if you want to win, of course, the best way to win is to break all the other candidates. And so here you can see how it works. This is a web page which was maintained by some Austrian colleagues, and then it kept track of the different attacks. And so what happened is that after almost 1 year, there were only 14 candidates remaining, the most promising, and then we spent like 3 years of cryptanalysis with many conferences, many papers, before NIST finally selected the winner, which was believed to be the most secure and with the best implementation properties. And so this winner, it was Ketchak, which was designed by a Belgian team. And so if you are a designer also, you would like your colleagues to have a look and try to break your cipher. So how do you do this? Then what you do is that you propose some prizes, and this was the case for Ketchak. So this is the announcement of one cryptanalysis prize for Ketchak. And as I said, this Ketchak function, it has been designed by Belgian colleagues, so the prize was beers. And so the announcement describes the special kind of beers they will give to the winner. And what happened is that we won the beers. And this was a work with my former PhD student, who's now a professor, Christina Bucha. And for getting the beers, what we did is that we published, or we observed a property what we call a distinguisher, which has a huge complexity. So this means that in practice, of course, this function is not broken, but this is a property which was not expected by the designers. Okay, so maybe some of you may wonder and may be a bit surprised, because usually when we speak about security of cryptographic primitives, usually we speak about quantum computers, because you can hear in the news that, well, the main threat against cryptography is quantum computing. So what's about quantum computer? Well, as you probably all know, we do not know whether a quantum computer will ever exist or not. But what we know is that if we can build such a computer, then it will speed up exhaustive search. That means that searching for one item within a set with n items, it will cost something which is roughly the square root of the number of items, and not something which is a number of operations which is proportional to the number of items. Well, this is not really a big issue, because for us in cryptography, this means that we will have to double the sizes of everything, double the length of the keys, and so on. So, well, that's a problem, but that's quite okay. Well, what is a more important issue is the fact that this quantum computer, we know that it will have a speedup, which is much larger for some specific problems. And among these problems, we have factoring and computing discrete logarithm. And these two problems from number theory, these two problems are the basis of the most widely used primitives in the class, in the category of public key cryptography. So this means that we need to design some alternatives to this widely used system in order to find and to have some public key primitives which we believe will resist a quantum computer. And this is called post-quantum cryptography. So that's very important for public key cryptography to design this kind of primitive. Well, I really believe that it's important, and actually this was the topic of my PhD thesis. But, well, I had to change, because at that time, it was the same time as the publication of Shor's algorithm on factoring. Well, this was a topic which was believed to be really marginal, and nobody was interested in that at all. So this means that it was very difficult to be published and to get funding on this kind of topic. And so this is why I moved to a different topic in cryptography. And, well, everyone in the area was asked to move to some more promising direction. And then, 10 years later, what happened is that NIST launched a competition on post-quantum cryptography. And then there was a huge, a huge pressure to move up to post-quantum cryptography. And fortunately, we have some colleagues that continue working in the area, even when during the years where there were no funding at all. So this is, I like telling this story because, well, this is something which is well known in sociology of science. This is called Matthew effect. So Matthew effect, it has this name after this sentence. What does it say? It says that in science and in research, well, the rich get richer. Well, you probably all know that when you start having grants, then you get more and more grants and funding. But what is probably a more important problem is the second part of the sentence, is that the poor get poorer. And so what does it mean? It means that when all the funding, it goes to a very few selected topics, then all the other topics, well, they don't get funding anymore, they don't get PhD students anymore, and then they will die, right? And so I think that as a scientific community, that's our responsibility to avoid this kind of thing, to avoid that some of the topics, well, die because they do not get funding, because research is research. Well, we don't know which direction will be, at the end, the most impactful one. And then we will get situations like what we have in this post-quantum cryptography. So let me now conclude. Well, if you'd like something to take away, well, on cryptography, maybe the main message is that we can only trust our cryptographic primitives if there's a public, important, and never-ending cryptanalysis effort. And all these three words, public, and important, and never-ending, all the three are important because this research is never-ending, of course, because we have some new ideas, publish new algorithms, and sometimes having new technologies like maybe a quantum computer. And so we have to, again, evaluate the security of our primitives. Also, we have new applications and then new types of primitives that need new cryptanalysis and so on. So this was for cryptography, but maybe you can also find some analogy between what I said on cryptography and what you know from your own research area. So for instance, that research takes time and needs time. I told you about our competition during 5 years for standardizing one primitive, but some of you maybe work on physics or chemistry and have some experiments, and so you also know that it takes time. Something else is that, research in all areas needs diversity of topics, diversity of backgrounds. Something that I find very important is that research is never a routine, and that's so nice. Research is, of course, very hard. You probably all know that, because it's intellectually demanding, but the counterpart of that is that it's intellectually rewarding, and this makes it very, very exciting. And so if I could give you a single advice, it would be that one. So please don't follow fads. Don't all move to AI because funding is there, for instance. Please work on what you believe is important and enjoy yourself, because probably it's the main ingredients for success in research. Thank you.
Thanks, Anne, for sharing your brilliant experience. At the beginning of your talk, I was motivated to invest in some cryptocurrency, but at the end, I thought maybe based on Matthew effect, I will become poorer. So let's start the graduation ceremony. In IP Paris, we have different programs, and we will do the graduation ceremony in 2 different series. So let's first start the first series, starting with economic graduates. So give it up for economic graduates, and we will announce the names.
For economics program, Professor Alessandro Riboni, Léa Bous-Lehmann, Pauline Carry, Germain Gauthier, Étienne Guigues, Randy Coty, Martin Munier, Elio Nimier-David, Justine Penaud, Estelle Remondeau, Yuanzhe Trang, Guillaume Thébotin. For Engineering, Mechanics and Energy program, Professor Jan Polder. Khadija Arjdal, Salwa Balan, Alexandre Barboni, Émilien Barou, Clément Bazin, Ilyes Berouni, Pierre Bernigaud, Alexandre Bleuzet, Aurore Cacas, Quentin Caradec, Quentin Chevalier, Julie Collignan, Madi Daey, André Dalmora, Élodie Doyen, Rodolphe Grivet, Zara Ousmanaour, Arthur Izikel, Arthur Julien, Eurial Kissinger, Léna Lequelec, Uthong Liu, Hassan Madkour, Geoffroy Magda, Ursi Makanga, Tom Marzin, Modou Mbaye, Zineb Meskin, Evangelos Mochos, Alice Nassor, Pierre Nibourel, Arthur Poulain. Clara Ramon Lozano, Marie-Laure Roussel, Aude Sani-Morté, Pierre Soljo, Kubra Sekmen, Usiang Shen, Lisa Sicard, Hector Solorzano Flores, Baris Telmen, Étienne Tixadou, Iman Tograe, Sinuen Jai, Carl Joe Armstrong, Théo Zurcher. Information Communications and Electronics Program, Professor Lyrida Naviner. Mohaddad Abou Romo, Natasha Al-Khatib, Yasmine Assioua, Jamal Darwish, Pierre Didier, Pierre Fano de la Horry-Clavier, Hakim Afidi, Seyed Faraz Jafari, Mohamed Eman Ktari, Guillaume Larue, I. Liu, Perrine Lognonnet. Alix May, Maxine Morenas, Nixon Mwansojo, Ruchirajan Shvitratva, Yuen Yao, Xiaoyan Ye, Badre Youssef, Juen Zhao. For physics program, Professor Davide Bocchetto. Bandar Albugami, Bahar Assadipour, Edmond Barat, Tarek Ben Sliman, Yanis Ben Kadoum, Ephraim Bernard, Pauline Besserve, Hugo Blanc, Pétrissor Gabriel Bléautou, Majdouline Borgi, Axel Buchot-Péraguin, Jafar Chakrani, Antoine Cordoba. Claire Darin Bapom, Vincent Dufoulon, Sébastien Extier, Carolina Garcia Soto, Renaud Gariou, Jérôme Garnier-Brun, Alberto Giampaolo, Javid Adjemati Dejan Ivanov, Paula Klej, Sami Lacal, Eric Liner, Nitin Malik, Robin Miquel. Jonah Mota, Federico Petronio, Matheus Povlansky, Miranzoa Aimé Rasolofo Manana, David Rivera Betancourt, Filippo Sotovia, Alessandro Tarabini, Elisa Tejeda Zakaria, Titan Loan Tong, Agatha Ulibari, Rang Yang, Longzhou. Humanities, Art, Literature and Languages Program, Anouk Daguin-Delin, Omar Layachi. Social Sciences and Management Program, Alice Karl, Anne-Sophie Dubé.
Congratulations to the graduates. During the period of your PhD studies, you may have experienced different stories. Sometimes you may have felt sad, sometimes happy, sometimes overwhelmed. Sometimes you may have felt alone. And sometimes you may have felt you have a lot of joy and liberty. But at the end of the road, when you look back, you see the beauty of the journey. I want to invite you, two PhD graduates, to come here and talk about their stories during their PhD studies. So I want to invite Lena Lekelek from Engineering Mechanics and Energy Department, and Baima Terkanji, graduate at Mathematics Department. Please.
So, ladies and gentlemen, esteemed faculty, proud parents, and fellow graduates, as I stand before you today, I'm filled with gratitude and accomplishment. My academic journey to this moment began in 2013, and in September 2023, after a decade of perseverance and dedication, I proudly became Dr. Lekelec. But please don't fret though, while I may be a doctor, my expertise lies in microphysics and biology, so if anyone studently feels faint, I must apologize, as I lack the skill to perform life-saving miracles. 10 years to obtain a PhD. It's certainly been a journey filled with challenges, triumphs, and everything in between. Allow me to take you on a brief tour of the milestones that have shaped my academic and personal growth. It all started at the University Paris-Sud in Orsay, not far from where we gather today, where I delved into the depth of fundamental physics, and here I stand, a decade later, with a PhD in biology. You might be wondering what transpired in between. After completing my undergraduate study in fundamental physics, I embarked on a new chapter at École Polytechnique as an engineering student. This experience broadened my horizons and revealed three pivotal truths about myself. Firstly, my affinity for applied biology. Secondly, my resonance with the school's value of collective contribution. And finally, my profound love for the Plateau de Saclay, its natural beauty, accessibility, and of course, its weather. Following these transformative years, I pursued a master's degree in microbiology in Paris and Edinburgh, just to come back after at IP Paris for my PhD. Within the confines of the Physical Microfluidics and Bioengineering Lab in Ladix and Pasteur Institute, I embarked on a journey of discovery and growth. I learned the art of making droplets, a very practical skill into everyday life. I learned to cultivate traits of autonomy, organization, and perhaps most crucially, patience, especially when experiments seem to defy all logic. I learned the profound importance of fostering a connection with colleagues, even amongst the tumult of a global pandemic that thought us to keep us apart. Finally, I learned that 2 months to write a manuscript is, in hindsight, a rather optimistic time frame. My apologies to all the supervisors who foresaw this outcome. All these lessons, though gleaned from the world of academia, have proven invaluable in my current position as a technical manager at the General Directorate of Armament. While my days now be filled with typical 9-to-5 routine, free weekends, and gratefully vacations, the essence of leading projects, charting my own course, and confronting my limitations remains unchanged. So here's to embracing the unknown, seizing every opportunity, and always acknowledging the profound impact of a journey well-traveled on the path of becoming a doctor, even if that doctor can't save you from a heart attack. Congratulations to my fellow graduates. May our future be as bright and promising as the path we forged together. Thank you.
Thanks, Anna. I'm really curious to know how you made droplets, but I will discuss with you later. So I wanted to invite Biomatter. Is he in the... Yes, please.
Good afternoon, everyone. It is an honor to share my testimony about my doctoral thesis with you today. I am Biomatter Kanji. First, I would like to introduce myself and talk about my academic path that led me to this PhD program. After studying actuarial science in Lyon at ISFOR, I was very interested in pursuing a career in finance, and that's how I had the opportunity to pursue a master's degree in statistics and finance at Institut Polytechnique de Paris. With advancing teaching, this master increased my interest in mathematics, especially for statistics, probability, and their application in finance. Given the quality of the teaching, and interested in the opportunity of pursuing a PhD in mathematics, I contacted two of my professors for a PhD opportunity at the Institut Polytechnique de Paris. They were very available to realize this project, whether it was defining the project research topic or finding funding. I conducted my thesis at the Center for Research in in Economic and Statistics, CREST, in mathematics applied to finance. During my thesis, I was interested in inferential statistics, ergodic theory, stochastic process with application in finance on the modeling of conditional volatility of graph type. I was very satisfied with my experience at IP Paris. At CREST, I benefited from the best support and guidance. I thank everyone who made this possible, especially my thesis advisor, who were very available and provided great support during the entire thesis. One thing I appreciated the most was the freedom I had to explore ideas, often in fields quite far from each other. Well, at the end, I have a problem to find the right subject for my thesis. And the opportunity to present my work in the internal seminar of the CREST and to get feedback from other faculty members and doctoral students. I also appreciated obtaining all the necessary funding to participate in conference or seminar nationally or internationally, and also not to mention the extraordinary administrative work that takes place at the global level of Institut Polytechnique de Paris. Also, I really enjoy working with my doctoral office colleague. We have all become very close friends. Even though we didn't not share the same thesis topic, we would often spend a lot of time, sometimes all afternoon on a board, on each other's problem to help unclog, and also help with proofreading thesis or a research article. After the thesis, I decided to join the private sector as a quantitative researcher on market risk, credit risk, or sustainable finance topics. My thesis experience and my doctoral degree from Institut Polytechnique de Paris allow me to position myself from high responsibility positions. I also enjoy living on the campus of IP Paris during my thesis, close to my lab, with a strong presence of international students, especially doctoral students. And I appreciated meeting people from different origins and cultures. In conclusion, this doctoral journey that we all share here was not just an academic adventure, but a true personal transformation. It introduced me to the joy of scientific research, especially in mathematics, and it taught me rigor and independence. Thanks to this experience, I feel ready to tackle railroad challenge, and I am very grateful for all people challenge and discoveries I have shaped that have shaped this journey, and I am excited to carry this learning into my future career. Thank you for listening.
Thanks, Mater, for sharing your experience. I agree, living on campus is joyful, except the weekends. So we are all alumni of Institut Polytechnique de Paris, and we should be connected still, and we should be connected to Institut Polytechnique de Paris. Sorry. I should announce the second series of graduates, starting with biology program.
For biology program, Professor Nicolas David. Christina Cardenal-Peralta, John James, Maxime Mouviel, Ivan Reveguc, Limé Zo. Chemistry program, Professor Cédric Tard. Christina Chebas, Louis Clavier, Weichu Fu, Meng Yu Gao, Nolwenn Mailleux, Christian Murga Cotrina, Ngoc Tram Phong, Hui Chiao, Antoine Roblin, Pauline Schiltz. Mathematics Program, Professeur François Rueff. Aria Akanva Foumani, Kossi Pierre Amenoa Badji, Kenes Asogba, Mathieu Barré, Étienne Belin, Thomas Bellotti, Sofiane Benzaït, Étienne Bonafou, Amandine Boucard, Mathis Chagneux, Qingkai Chen, Francesco Clérici, Max Cohen, Bénédicte Colnet, Tiphaine Delaunay. Clément Deslandes, Étienne Daunier-Méros, Claire Écotière, Lucas Erzbischoff, Jean-François Fritsch, Morgane Guabert, Quentin Jacquet, Yazid Janati El Idrissi, Pablo Jiménez, Maxime Khaledine, Baye Matar Kanji, Rémi Leluc, Clara Leparou, Krang Liu, Antonio Lopez Newman, Ariana Mingonet. Paul Monchot, Lucie Nérac, Vincent Placier, Solange Pruil, Gabriel Romont, Luis Rosas Martinez, Othman Saki, Meyer Sedbon, Flore Saintenac, Vladimir Zvikin, Émilie Tézénas Dumoncel, Christophe Wong, Wanchin Wang, Jui Yang, Younes Yousfi, Jue Yuan, Tianfei Zhang. Computing Data and Artificial Intelligence Program, Professeur Amal Benzegoub. Raphaël Hdou, Eduardo Alvarado, Ekaterina Antonenko, Abaya Datri Arij, Gaël Atep Gatche, Reda Ayassi, Rita Azi, Carlo Alberto Maria Barbano, Ayoub Ben Hammer, Ruta Binkinte Sadoskien, Sayan Biswas, Maxime Bombard, Armand Bochine, Lies Bouchama, Dimitri Boucher, Mohamed Bouchouya. Federica Granez, Raphaël Hdou, Eduardo Alvarado, Ekaterina Antonenko, Abaya Dratri Arij, Gaël Atep Gacho, Reda Ayassi, Rita Azi, Carlo Alberto Maria Barbano, Ayoub Benhammer, Ruta Binkinte Sadoskien, Sayan Biswas, Maxime Bombard, Armand Bochine, Lies Bouchama, Dimitri Boucher, Mohamed Bouchouya. Lorraine Brisatier-Porchon, Théophile Cabane, Hassan Chaïtou, Pierrick Chatillon, Yanis Chemli, Lirou Chen, Marine Collery, Maria Luisa Costaviana, Ganesh Del Grosso Guzman, Nathaël Denis, Yanis Djebra, Nicolas Donati, Rémi Dulong, Maxime LKL, Abir Fatala, Thomas Feltin. Federica Granez, Antoine Henry, Marc Hulsel, Roman Niazev, Meriana Kobesi, Chrysoula Cosma, Anne Kwam Djoune, Ariel Kwiatowski, Maud Lastic, Min Hong Le Nguyen, Anatole Lefort, Thibault Lelong, Nan Li, Seibin Lim, Gentiao Liu, Mathis Maillard, Matteo Manighetti. Félix Mathieu, Inès Meramouya, Thomas Ménard, Mariem Mesgani, Martin Milovanovic, Abhishek Kumar Mishra, Marianella Evelyne Morales-Elena, Alexandre Moreau, Luc Motet, Jiti Omidvar, Vendla Sida Wedraogo, Kauter Wenich, Antoine Oustri, Olivier Palanca, Génel Parek, Louis Péné de Monternon. Constantin Filipenko, Carlos Pinzon Henao, Johan Pipero, Danny Chiu, Ming Chiu, Ibo Chuen, Nedeljog Radulovic, Ena Toki Rasoa Manana, Camille Rupli, Angelo Sade, Wenhao Shao, Yanis Tevisen, Marcelin Tworski, Ali Bora Ulusoy, Tiai Wei, Li Dingxu, Zheyuan Yao.
Congratulations. Now the view is a bit different. I see a lot of yellow colors. Yes, I was saying this. We are alumni of IP Paris, and we should be connected through the association of the alumni. So I want to invite Nancy Ngoun, president of the IP Paris Postgraduate Alumni Associations. Please welcome.
So dear graduates, family members, and friends, I would like first to extend my heartfelt congratulations to each and every one of you. Today is a testament of your hard work and dedication. My name is Nancy Ngoun. I'm an alumna of the Master in Energy program of 2020, so it was the first generation of Master in Energy of IP Paris. And since the creation of IP Paris, we have been missing kind of a platform, a center, a central unity to gather all of our growing community of alumni. So that's why today I'm happy to stand before you as the president of the newly formed IP Paris Postgraduate Alumni Association. So our aim is to provide a platform for interaction and create a sense of belonging to IP Paris. Networking, mixers, career panels, mentorship programs, alumni reunion, you name it. We have plenty of ideas to create meaningful experiences for your personal and professional growth. And whether you become exceptional engineers, scientists, researchers, startup founders, or CEOs, I invite you to join us on this journey because you all have a role to play in uplifting IP Paris and its alumni network. We really hope to create a robust international network that will promote the reputation of IP Paris in France and also abroad. You can follow our LinkedIn page by scanning the QR code. You'll stay connected with us and you will receive updates on our events and activities. And after the ceremony, we'll have a booth at the cocktail reception, so please come and talk to us. Let's get to know each other and maybe see what we can do together for the association. And before leaving the stage, I would once again want to congratulate you on this milestone, and I want to wish you all the best for this next chapter of your lives. I look forward to meeting many of you at the booth later. Thank you very much.
Thanks, Nancy. I had the chance to attend a few PhD defense at IP Paris, and I enjoyed all of them, considering the high quality and high standard research produced, and also the way you have conveyed it. And I'm sure that's the story of every single research work of you. Some of you have been applied for the IP Paris PhD Thesis Award, and it was really a hard work for the jury to choose 7 awardees among all of this high quality work. And I want to invite Professor Adriana Tapus and Professor François Rueff to come to the stage and nominate the 7 IP Paris PhD Thesis awardees.
Okay, so IP Paris awards annually show the best thesis award to the students who have produced the best PhD thesis and made the most outstanding contribution. So this year we received 50 applications, all of them of high quality. So the jury had really a hard time to deliberate. And this year we have 1 IP Paris Best Thesis Award and 6 department Best Thesis Awards. So the IP Paris Best Thesis Award is given to Nolwenn Mailleux from the chemistry department for her thesis entitled Synthesis, Redox Chemistry, and Electronic Structure Investigation of lanthanide complexes with aromatic ligands of various sizes and bulkiness. Very long title. So, unfortunately, she's not here with us because she just started her postdoc position at Berkeley. So, but she sent us like a very nice video that we're going to show in a few seconds. So I will start, we'll start first with the presentation, and after that I will announce also the department Best Thesis Awards. So the Best Thesis, so we can start right now, so with the video of Nolwenn Mailleux.
Hello everyone. I would like to start by thanking the PhD Award Committee for recognizing this work. It is an honor to receive such a prize on a project that means so much to me. Unfortunately, I cannot be with you all to celebrate today, as I recently started a postdoctoral position at the Lawrence Berkeley National Lab in the US. I would like to thank the Doctorate School for still giving me the opportunity to share this quick video with you today. I just wanted to present the topics that I've studied over the last 3 years. As any PhD thesis, the title can get quite technical, but some of the basic notions can still be very interesting. The main actors of my PhD were the lanthanide elements. They are not the most famous one, but you can find them at the bottom of the periodic table. They are sometimes called rare earth metals, which is a misnomer as they are in reality quite abundant in the Earth's crust, some of them being as abundant as copper. They are often found as mixtures of different lanthanides, which can then be purified and used for a variety of applications. Even if you don't know them, you have probably interacted with them, as there are luminescent europium agents used for counterfeiting measures on euro bills, gadolinium complexes are powerful contrast agents for MRI, and neodymium is an essential component of the magnets used in wind turbines. As you can see, they are of great importance in the industrial world, so what do we do with them in the lab? I have selected 2 different projects to give you a general idea of the questions that can be tackled. First, we have used a thulium-containing species showing high reactivity towards small molecules. Particularly, they are able to trap carbon monoxide through a redox mechanism. This new complex is then quite reactive toward carbon dioxide molecules and can incorporate them to form a new organic compound. This project shows that the lanthanide elements can be used in the valorization of simple and even sometimes harmful gas to transform them into useful products. Another possible path is to try and harness the physical properties of the lanthanides. Notably, they are involved in a lot of development towards quantum information science as ideal candidates for the making of quantum bits and atomic size magnets. Specifically today, a lot of the data storage relies on the use of magnetic devices where the amount of storage is limited by the size of the magnetic domain. It has been shown that under specific conditions, lanthanide complexes can possess a spin at a molecular level, making them effectively the smallest magnetic domain possible, with value of either 0 or 1, depending on spin orientation. As such, in the lab, we have investigated the type of arrangements that lead to this behavior. The study of the electronic density presented at the bottom of the screen helped us to propose different targets that were then shown to behave as single molecule magnets. To conclude, I hope that I was able to show you that these elements are everywhere and possess very interesting properties. So much so that they can be used to tackle a lot of the problems that the world faces today. And with that, I will quickly finish by thanking once again the PhD Award Committee, and of course, all of the people that helped me throughout my PhD, my supervisor, Dr. Grégory Nocton, the Lab 1 team, the whole LCM lab, the collaborations, my family and my friends, of course, and I would like to thank you all for your attention. Congratulations on your graduation, and I hope that you have a great time.
So now we go. So the award for the best thesis award for the Department of Information Communication and Electronics, it's awarded to Nixon Mwamsojo for his thesis entitled Neuromorphic Photonic Systems for Information Processing.
Hello, everybody. My name is Nixon Mwamsojo, and today I'm going to present you my PhD work, which was titled Neuromorphic.
Hi, everyone. Thank you very much for having me, and thank you to all the members.
I'd like to thank the member of the jury for this opportunity to share my work with such a brilliant group of graduates. So what motivated me to embark on this journey was the current tendency of AI, where we focus solely on performance of the models and we don't stop and think how much do we spend or how much resources do we put on the models we proposed. And for this one, it was this paper that really struck me like heavily. It's when I learned that some models, to train them fully, to have a good performance, you have to spend as much energy, you have to emit as much carbon dioxide gas and greenhouse gases, as much as 5 cars in their lifetime. And this was very interesting as a remark for me, and at this time I had already started working on reservoir computers. So what we started to work on, we decided to embark on this journey of proposing reservoir computers as a solution for various problems. And a reservoir computer is actually a framework for recurrent neural networks that simplifies training. And we do that by not training the entire neural network, but choosing specific parts of the network to train. And even further, to even gain more on the energy consumption, we focused on photonic implementations of reservoir computers. And the good thing about reservoir computers, you can do them with most physical systems. For us, it was photonic hardware. Why do we choose photonics? It's because photonics is quite efficient. Optical technology has maturity and is quite efficient. And also because we can benefit from the speed and the parallelism of photonic systems. And of course, a reservoir computer has inherent properties of speed in training. And to give you a glimpse of types of tasks briefly, we worked with data from Broca Hospital. And this data consists of patients, senior patients, who were asked with various tasks of copying and writing and drawing on a tablet. As an example, for example, they were asked to plot, to draw a cursive L, like I show here. And we proposed various systems, among them including reservoir computer. What we observed is, and this was what we wanted to say through our thesis, is that we had an accuracy of 85% in the classification error, in the classification of the detection of the disease. But this one was less compared to, for example, other methods that are well known in the literature, like bidirectional LSTM or other LSTMs or convolutional neural networks. But what made our approach a little bit interesting in this case, even though it has slightly less performance, is that we served by a factor of 8 the amount of energy and computational power we needed for attaining this performance. And of course, we implemented this in simulation and then we did it in an experimental implementation, and we had a potential to even have more gains in terms of savings in complexity and energy. Another task that we tried to use photonic neural networks to implement was the task of image denoising. And in this case, we tried to have an image that is noisy, like we show here on the left, and then using a photonic circuit, we tried to obtain an image that is much cleaner, as we can see on the right. And this one, we proposed 3 systems. The first one is Hopfield neural network, which was implemented both in numerical simulation and hardware setting in our lab. And we compared with well-known, like simulated annealing, as I show in this small plot. And as we can see, our system converged very quickly, both in numerical simulations and in photonic implementations in the lab. And of course, while we were working with these tasks, we quickly realized one thing. It's very hard to optimize these systems. So we decided how maybe we should propose a method that can be used when you are in an experimental setting to tune or fine-tune your model. And for this one, we proposed a stochastic gradient-based technique that can be used to agnostically tune the parameters of your model. And we used this one to tune every time we had a different task, we had a different application, we used it to tune. And what we observed was consistently, we only use 29% of the number of iterations or cost function evaluations we would need for SUN. And we would also use around 7% of the resolution we would need for grid search. So that's a brief summary of what I did during my PhD. But all this wouldn't have been possible thanks to these incredible people who have been very helpful during my thesis. Every time I had a problem, every time I was stressed out, I would reach them out, and they have been very, very, very helpful and instrumental to accomplish this. And I'd also try to thank my friends who are in the audience and my family for coming on this day. Thank you very much.
So you can see how passionate are our PhD graduates, even during the graduation ceremony. So I think right now, I'm going to give the name for the best thesis of the Department of Computer Science, Data, and Artificial Intelligence. And I think this award is going to, our keynote speaker is going to like it very much. So it's given to Maxime Bombard for his thesis entitled Structured Codes for Cryptography from Source of Hardness to Applications. Maxime.
Well, thank you very much for the award, and thank you very much for the introduction. Yeah, let's go. So, well, cryptography is the science that studies the protection of private data. And it's especially important when we need to send sensitive information over the internet. For example, when you want to do a transaction online or to contact your bank, or, I mean, you need to send sensitive information. One of the main building blocks of cryptography is known as public key cryptography, and you've heard about it in the talks of Anne Canto. And, well, the security of those cryptographic schemes, they rely on the hardness of computational problems from different fields of mathematics, such as integer factorization and so on. For example, if I ask you to find two integers such that their product is 15, you will immediately say, yeah, 5 and 3, of course. But if I give you a number of like 600 digits, it's much harder, unless you've got a quantum computer. Therefore, I mean, we know that since the 1990s that the cryptography that is currently deployed nowadays, it's completely broken once we have access to a large enough quantum computer. And therefore, we need to find new mathematical domain to build on. And during my PhD thesis, I was interested in one domain known as error correcting codes. And more specifically, an object called structured error correcting codes, which enable fast and cryptography and post-quantum cryptography. However, when you add some structure, you improve the efficiency, but the security is less evident. And earlier in the talk of Anne Canto, she talks about cryptanalysis, which is one way of assessing the security, but sometimes you introduce new problems and you don't want to spend decades to try to break them. So we rely on proofs, and when you add some structure, the proof is less evident. And in my PhD, I tried to bridge the gap between efficiency and security by like developing new tools for creating proofs of security in structural error correcting codes. Well, thank you for your attention.
Okay. So right now, we go to the Best Thesis Award of the Department of Economics. It's awarded to Elio David Nimier for his thesis entitled Firms, Territories, and Inequality. Unfortunately, he couldn't be here with us because he just got a position as an assistant professor at the University of Columbia. But he sent us a video.
Hi everyone, thank you very much for having me, and thank you to all the members of the jury, member of IP Paris, CREST, and of course my advisor, Francis Kramartz. So my thesis is entitled Firms, Territory, and Inequality. It is at the intersection between labor and spatial economics, the underlying question being, can we promote economic growth while at the same time reducing inequality? So the first chapter is about providing new data on local and national inequality in France. The second studies policies that redistribute profits within firms. And finally, the third chapter sheds new light on the role of local human capital for economic activity. So starting with the first project, Inequality and Earnings Dynamics in France, this is part of an international project that gathers more than 50 researchers working in 13 countries. This project has two main objectives: to document earnings inequality over time, and second, to construct harmonized measures between these 13 countries. So what do we learn? First, we find that France is the only developed country that experienced a reduction in earnings inequality. This reduction is driven by labor market reforms, such as the large increase in the minimum wage and the decrease in the work week, but also driven by a gender convergence with a decrease in the gender gap. Finally, we also show that there is a convergence between cities, with poorer cities catching up with richer ones. The second paper studies the effects of mandatory profit sharing. In the case of France, since 1967, firms above 100 employees have to redistribute a share of their excess profits to their workers. This is called the participation salariale. And we explored a reform in 1990 that decreased the size threshold from 100 to 50 employees. We find that profit sharing is large. It redistributes about 13% of pre-tax profits. It acts mainly as a within-firm redistributive tool, meaning that it takes profits from the shareholders, and give it to the workers, but has very little effect in terms of economic activity, including productivity and investment. Finally, there are also evidence of firms implementing strategies in order to avoid paying profit sharing, which introduces some distortions. Finally, the last chapter investigates the role of regional universities in fostering local economic activity. And I study a massive college expansion policy, the Plan Université 2000 in France in the 90s. It resulted in the construction of about 350 new colleges in more than 150 cities. And I show that this fosters local economic growth, driven by the entry of new productive firms, and at the same time, the exit of older, less productive ones. However, despite large gains, I see an unequal distribution of these gains with positive effect for the young workers, but negative effect for older workers. Thank you very much for your attention.
Okay. So the best thesis of the Department of Mechanics and Energetics is awarded to Rodolphe Grivet for his thesis entitled Contact Line Motion and Solidification. Rodolphe, please come on stage.
Hi, everyone. My name is Jafar, and I did my PhD.
So, hi, everyone. My name is Rodolphe Grivet. I was a PhD student here at l'ADIX, at École Polytechnique, with Christophe Josserand, Thomas Séon, and Axel Huer. And I also worked with lots of people from different labs that are here and that I would like to thank. So my thesis was about contact line motion and solidification, which is part of a broader topic in fluid mechanics, which is the freezing of capillary flows, and which has applications in various domains, from aircraft icing to the understanding of natural flows, such as icefall morphogenesis. We're interested in that because it gives rise to very complex and beautiful shapes. Here I just pour some yellow water on a cold plate, and you see that you have these nice patterns that are formed. And one way you could understand that is by simply considering that you have two boundaries that are moving, the free surface of the flow, which is subject to the capillary force, and the ice-water interface, which grows. But at some point, these two boundaries, they intersect each other, which we call the contact line. And my objective in the thesis was to investigate the interaction of this moving contact line with the solidification through experiments. So the first thing I did with Antoine Monnier was to investigate the spreading of drops of water on cold surfaces. And you see that as the surface gets colder, the drop gets arrested sooner. And in fact, we showed that this is due to the growth of ice crystals, which you can see if you look from the bottom. You see ice crystals growing within the drop, and that arrests the contact line. Then I continued with drops, looking at drop impacts on cold surfaces. And you see that when the surface is colder, you eject more droplets, which we call the splash. And we found that this behavior on ultra-cold surfaces is very similar to what happened on superhydrophobic surfaces at ambient temperature. So, which makes an analogy between ultra-cold surfaces and superhydrophobic surfaces. And then I'll move very quickly on that because there's no video. But I used an old problem from Landau, Levitch, and Deryagin in the 1940s, which I adapted to the case of solidification in order to measure the contact angle, so basically the boundary condition you need at the contact line. So to measure the contact angle between water and ice, to conclude that, in fact, water does not completely wet the ice. And finally, with Vladimir Sarlin and an intern, Julien Sou, we investigated what happens when a hot droplet impacts an ice cube, and this gives rise to some also very nice videos. And I will leave you with these beautiful pictures and beautiful physics that I came by during my PhD, and I thank you for your attention.
Thank you. And now I'm going to announce the awardee of the best thesis of the Department of Mathematics. So the best thesis award is going to Meyer Sedbon for his thesis entitled Causal Inference through Optimal Transport.
Thank you for the introduction. Hi everyone, so my name is Meyer Sedbon, and today I'm going to speak about some of my work that I've done during my PhD on Lorentz structures, advanced in optimal transport Lorentz structures and application machine learning. So let me briefly introduce what is optimal transport. So optimal transport is basically a tool that allows you to compare two distributions. And the way optimal transport will compare those two distributions is by trying to send one into the other. So more concretely, here I represent two distributions on the left side as a pile of sand and on the right side as a whole. And here we will assume that they have the same volume. And basically, optimal transport will try to send all the sand to the hole in an optimal way in order to fill the hole. And as you may see, there are many strategies in order to fill the hole with the sand. So if we take a specific location X, at this location, we might have a certain amount of mass denoted by the mu of X. And let's say we send a certain amount of mass at location Y and the leftover that we have at location X to the location Y prime. And if we do that for any point X where we have some sand, then we might define a full strategy to send the whole sand to the hole. And that is denoted by the P here. And therefore, optimal transport will basically try to find among all the possible strategies the one that minimizes transportation cost. However, in practice, especially in data science, we often deal with discrete data. And therefore, we need to, if we want to apply optimal transport in order to compare objects, we will need to solve a network flow problem, which might require a supercubic complexity with respect to the number of points, the number of data points that you have. And therefore, this prevents us to apply it for a very large-scale problem. On the other side, we have also another limitation of optimal transport is that it suffers from the curse of dimensionality in the sense that if you try to estimate optimal transport between two distributions that lies in a high-dimensional space, then the rate of convergence of your estimator will converge exponentially slowly with respect to the dimension. So in that sense, optimal transport is not very useful for machine learning application, at least as it is. And so during my PhD, we proposed a new regularization scheme of the optimal transport problem, which instead of considering all the possible strategies that one can use in order to map one distribution into another, we regularize the space by considering only the one that admit a low rank in the distributional sense. And this defines the optimization problem that we study. And those are the results we obtain. So concerning the two problems I defined earlier, we obtained the two improvements. So first, in terms of computation, we managed to reach linear complexity in terms of solving the optimal transport problem under low-rank constraint, meaning that we are now able to solve the problem for very large-scale problem with millions of points. So that's the setting usual in machine learning nowadays. And another result is that the rate of convergence of the estimation of Laurent-Coty is not completely dimension-free, meaning that even in the high-dimensional setting, you can still estimate correctly as long as you have enough sample to the low-rank optimal transport. So to conclude, low-rank optimal transport allows to apply ID from optimal transport in the large-scale and high-dimensional setting, which might be beneficial for machine learning problems. Thank you very much for your attention.
Thank you very much. And now, last but not least, so the best thesis of the Department of Physics, it's awarded to Jafar Chakran for his thesis entitled Towards a Complete Understanding of Neutrino Nucleus Interactions with the Upgraded T2K Near Detector. Very complicated. So, again, so unfortunately he couldn't be here with us. He just started also in the same place as our IB Paris Best Thesis Award. So he started a postdoc position at Berkeley. So now we'll see the video.
Hi everyone, my name is Jafar and I did my PhD at Laboratoire Le Prince Ranguet on neutrino physics. Neutrinos are a type of elementary particles that is super fast, super light, and super hard to interact with. But one of their mysterious characteristics is that how they change identities. Any object, whether it's a table or a ball or a chair, maintains its identity whether you're using it or not, right? Even electrons, also elementary particles like neutrinos, keep the same identity whether they're in an atom or freely streaming. But this is not the case for neutrinos, which can change their identity as they travel in space. This was experimentally confirmed not so long ago and was awarded the 2015 Nobel Prize in Physics. But since it is a recent discovery, we still don't know much about why this happens. I worked on the T2K experiment located in Japan, which aims at precisely measuring these identity changes, or what we call neutrino oscillations. The way this experiment works is the following. We have a particle accelerator in the east coast of Japan that produces an intense neutrino beam, and right at the production point, we have a suite of detectors that tries to characterize this flux of neutrinos before they get the chance to oscillate or change identity. Then we measure them close to the west coast of Japan in the Super Kamiokande detector, which is a huge water tank of about 50 kilotons of ultra-pure water. My work particularly focused on the upgrade of the near detector, which uses a novel technology to precisely track the particles that go through it and measure the neutrino interactions. These use complex readout electronics that we actually developed and tested right here in the lab. With this upgrade, we hope to shed the light on one of the biggest mysteries about the universe. We have indications in our old data that the way neutrinos and antineutrinos oscillate could actually be different. If we are able to measure this difference with the upgraded new detector, we could help explain why the universe is dominated by matter and not antimatter, which is one of the long-standing questions in physics. This would allow us to even further understand the origin of the universe.
So now, I would like to invite President Thierry Coulon, Anne Canteo, our keynote speaker, and Kes van der Beek here on the stage, and also the awardees to come here to receive their award. I would like to congratulate you also one more time. Okay. And now I would let Thierry Coulon, the president of IP Paris, to say the final words. Thank you.
Thank you very much, Adriana. Dear PhD graduates of IP Paris, a lot has already been said, especially on your merit and achievements, I would just like to add 3 remarks. First, at IP Paris, we have strong ambitions, very strong ambitions. We want to become a first-class world player in science and technology. Our benchmarks are Caltech, MIT, ETH, EPFL, Technion. It's a tough task, but we do have the potential to achieve this. Second remark, PhD is a lever to build our institution and to achieve this ambition. Of course, if you want to become a worldwide known university, you'd better have a PhD. But if you want to transform outstanding engineering schools like the ones that are members of IP Paris, okay, you have extremely strong students, you have outstanding academic staff, but engineers would better become, at least for a large proportion of them, doctors. And that's the case at IP Paris. We are soon going to reach 30% of our engineers doing a PhD. So that's a level of transformation. The third remark is that from your point of view, PhD is, of course, an opening key to the academic world, but not only. It's an opening key to the academic world because we guys are soon going to retire. I mean, many people in academia will retire, and we will have a need for young people starting the career. And the second point is that it's not only an open key to the academic world, it's also a key to the economic world. Why? It's because economy is transforming now. Our economy is an economy of innovation. And whether we are talking of large companies, of startups, they do need you. And finally, I mean, one story. You know, I have a life, and during this life, I think about transformation of higher education in France. And there is a seminar at the École Normale Supérieure, often on Fridays, and this morning there was this seminar. The question is, I wonder, what is the impact of you guys, of your thesis? So, wait a minute. This morning there was a seminar on a connection between education and economic growth. And the scholar who was talking was Xavier Jaravel. And at some point, I mean, you know, I was in the transportations following the seminar on my phone. And at some point, I hear that he quotes the PhD work of a guy at IP Paris. And this guy was Elio Nimia David. So I'm very pleased this afternoon to learn that, and I said, well, looks quite interesting. You know, you remember he connected the local economic growth with the Plan Université 2000. I mean, I was quite interested, of course. So yes, you do have an impact. I only take this example that happened to me this morning. I'm sure that given what we have just listened, you will have impact. So finally, be ambitious, we need you. I mean, climate is a problem, health is a problem, society is a problem, geopolitics is a problem, and we need science to solve this problem. Be free, of course, and I'll finish by thanks, of course. Thank you to the academic staff. I mean, you deserve a lot. You help these guys, these brilliant minds, a lot. Thank you for the graduate school staff for the organization of this ceremony, and thanks to you and your family. And finally, final message, give us some news through the Alumni Association. We want to know what you have become, what are your careers like, and please advocate IP Paris. I mean, we have joint interests. The more you succeed, the more IP Paris is famous. The more IP Paris is famous, the more you succeed. But it's just not only joint interest, it's just because we all think that we can bring something to the world. Once again, congratulations.
Thanks, Professor Coulon. So we are at the end of the ceremony. I want to appreciate all the speakers, all the organizers, everybody who came to this beautiful campus today. Congratulations again to the graduates. You have arrived to the peak of the mountain, but it's start of many. So keep up the good work, and I'm sure that every single of you will be effective people on whom the society will count. Before going for the cocktail, which I guess many of you are waiting for, to be honest, me too, I want to invite all the graduates and directors come on the stage, having a memorable photo and perform the traditional ceremony of cap tossing.